Okay. For my part, I'm gonna talk about this modeling the motion. Okay, as we know, bungee jumping is the one dimension with respect to time can be broken into two different sections. So I'm going to divide into two different sections, which is before the person jump and after the person hit the bottom. So so I'm going to talk. The formula is total force equal to mass times acceleration. Okay, to describe how the bungee cord will pull on bungee jumper, we will use Hooke's law because the relationship is said to be F equal to negative kx, where k is a constant that is specific to the spring. The stress is said to be force applied on the object divided by cross-sectional area of the object, which means we cut the rope and we count how we do the math on the area of the rope. The strength is said to be changed in length divided by the initial length, and it will result to Young modulus, which is the formula is y equal to f over a over divided by dl over l. Okay. Next, Young modulus is a constant for a given material. F is the force, A is the area, L is the length, and the L is the change in the length of the cord once it has been stretched. This look like a Hooke's law if you remember that the L and the X from Hooke's law have the same meaning. So we derive the formula equal to F equal to AY over L times X. The Young's modulus constant, the cross-sectional area and unstretched cord length will not change for any given cord. So we can say that the spring constant in Hooke's law is K equal to AY divided by L. Okay, so we cannot do the math like this. So in order to keep the math doable, we will also stick to wind resistance that is linearly proportional to the velocity. So force wind resistance equal to negative beta times V. This V also downward is equal to positive value.
Hello, my name is Warren. So here I'm going to talk about free fall. When the bungee jumper first jumps off the bridge, they will have these two forces, which are gravity and the wind resistance, which is negative beta v. So the force of gravity is positive because we define that the positive x direction is to be going down, and the wind resistance is negative beta v because the force of wind resistance is always in the opposite direction of the velocity. So by using Newton's second law, mg minus beta v equals to ma, and using the fact that a equals to dv over dt and v equals to dx over dt, and a little algebra, we can put this into the form of an inhomogeneous equation, which is shown this one. So next, we're going to solving the homogeneous equation. So in order to find the general solution of the inhomogeneous equation, first we must find that the solution to the equivalent homogeneous equation. In other words, we will set the driving force G to 0. So here are the second derivative of dx over dt plus beta over m times with dx over dt equal to 0. And the characteristic equation for the homogeneous equation is p lambda equals to lambda square plus beta over m times lambda. Next, in order to find the roots of the equations, so we can set p equal to 0, and we can get first lambda equals to 0 and second lambda is equal to negative b over m. And the solution to homogeneous equation is equal to x equal to c1 times exponential of lambda 1 times t plus c2 times exponential of lambda 2 times t. And by substitute in our values for our lambda, x equal to c1 plus c2 times exponential of negative bt over m. So now the homogeneous equation has been solved, and the only thing left to find is particular solution. So based on equation 2, which is this one, all right, and we look at the driving force that is on the right hand side, then we see that the driving force is a polynomial of 0 degree, which is a constant. Okay, so if we see that a particular solution is this one, x h equals to a times t plus b, and d over dt times xp equals to a, and second derivative of d over dt times xp equal to 0, then we can plug this into the equation to answer for a, and we can find that a equals to mg over beta. So finally, our general solution is will become this one, x equal to c1 plus c2 times with exponential of negative bt over m plus with mg over bt times with t n plus b. So c1 and b are both constants because c1 is an arbitrary constant. We said that it accounts for b, and the x will become this one is equal to c1 plus c2 times with exponential of negative bt over m plus with mg over b times with t, because b is constant. Thank you.
Now we proceed to below the equilibrium point for the kite. When the bungee jumper is below the equilibrium point, we must now find an equation of motion. We call Newton's second law, F equal to ma. However, they are now subjected to the force of the cord pulling on them. The force exerted by the bungee cord is negative kx according to Hooke's law. Using this in conjunction with Newton's second law, mg minus beta dx over dt minus kx equal to md squared x over dt squared. Then we rearrange algebraically to look like an inhomogeneous equation like this. So we go to solving the homogeneous equation. The first step to solving the homogeneous equation is to solve the equivalent homogeneous equation. So the characteristic of equation is p lambda equal to lambda square plus beta over m lambda plus k over m. So we set p lambda to 0 and we use the quadratic to find the root of the characteristic equation like this. So we assign equation this, equation 4. There are three cases when b over m square minus 4k over m is greater than 0, equal to 0 and less than 0. So for bigger than 0, so the case is over them and the solution will not oscillate. If bungee cord and jumper system fall into this category, then there is a problem because the bungee jumper will likely experience too much acceleration. The characteristic equation has two distinct roots, so the solution will take the form like this equation. Now we can plug in our expression for lambda to get this equation. So we go to the case 2 where equal to 0. This case is critically damped and its solution appear very similar to the overdamped case. The characteristic equation has one real root and the solution will be like this or be like this. Remembering that in this case is equal to 0, we say that lambda is equal to negative beta over 2m and that our solution will be like this. So in case 3 is less than 0, so this case is underdamped and oscillate. The solution in this case will be a combination of the real and imaginary part of exponent lambda t. First, we split up the exponent like this. Now we go to exponent bit split up into cos bt plus I sin bt. So we get the equation like this. The real part of the equation above is exponent at cos bt, while the imaginary part is exponent at sin bt. If plug in the lambda value, then we got the equation 4. And we use the same process to separate out the real and imaginary part. Then we get the real part of exponent lambda t is like this. So why the imaginary part is like this? Then homogeneous solution will be combination of the real and imaginary part of exponent lambda t. Like so, this is the final equation. Now we solving the particular solution. The next step is to get the particular solution of the imaginary equation equal to g. The driving force is a polynomial of 0 degree, just like it was for the free fall equation. We can assume that solution is some polynomial with unknown coefficient. Then plug in the solution into the equation above to find those coefficients. So we just plug in this homogeneous equation from this to this. Then because there is no t term, the coefficient alpha must be 0, and as a result like this, then we manipulate b, then we get the particular solution xp equal to gm over k.
Assalamualaikum and salam sejahtera. After all the general solution we obtain above, we can solve it without using a numerical solver. In this part, we have to divide a bungee jumping into three parts, which is setting the variable before the cord start to pull and after the cord start to pull. Firstly, when we want to setting the variable, we need some initial condition and parameter. We are going to model an 80 kg man jumping off a bridge with a height of 100 meter with a 30 meter long bungee cord with a diameter of 0.00635 meters. Using a Young modulus formula, we can measure a bungee cord that have a same thickness with a length of 1.31 meter and force of 10 Newton was applied, and 0.16 meter is a stretch cord. Maximum stretch of cord is 220 meter. Using a Young modulus formula, we can get the value of Young modulus here. We will assume that the cord that we measured is suitable for bungee jumping. With this assumption, the K value that is used in Hooke's law will now be determined. Pulling from equation this, we can get the value of spring constant in Hooke's law. Now we have all but one variable, which is beta. To do this, we go back to F equal to ma and look at free fall, which is this equation. Because we're looking at when the person has reached terminal velocity, which is no change in velocity, we can set dv over dt to 0 and solve for beta here. According to hypertextbook.com, a good approximate of the terminal velocity of a person is 60 meter per second. With this, we get the value of b. After that, the next condition is before the cord starts to pull or before a person start to jump off bungee jumping. Now that we have all of the variable, we can use the general solution that we found earlier. First, we will use the initial condition of x to 0 equal to negative 30, which is mean that 30 meter above the equilibrium point of the unstretched cord, and v0 we get 0. The initial value of t has to be 0 since x0 and y0. Using equation this, to make it more easier, we replace beta over m with a to make the next step easier. And differentiating this, we get this equation. And if we use the initial condition above, we get these two equations. Then it can be simplified to these two equations. Next we can solve for C1 and C2. And if we plug in the known values for our parameters and condition as stated before, we can get the value of C1 and C2. So the equation of free fall becomes this. From this position function, we need two things. First, we need to find when x is greater than 0, because this is when we need a new equation to represent the bungee jumper. Second, we need to find the acceleration as a function of time. From the graph of position function, it seems that x to t equal to 0 when t 2.67 seconds. If we plug this and all of our known into the velocity function, which is this, then we get that v when 2.67 equal to 21.22. We will need this velocity as well as t equal to 2.67 for the initial condition of the next equation. And the last condition is after the cord starts to pull, which is after the person start to jump the bungee jump. To solve this part of the situation, we still use the same parameter but different initial condition and equation. To make the solution easier to find, we will say that the time 2.67 seconds for the previous equation is at 0.67 is at 0 second for the new equation. The position and velocity stay unchanged however. For this part of problem, we need to decide which case to use. If we plug known values into this, then we get negative 0.098, which means that we must use case 3. Our solution for x is a combination of both the solution in case 3 and the particular solution. This is the first equation, and it will become easier if we let a equal to this and b equal to this, and the equation become this. And if we differentiate this, and we can get the next equation, which is this. Next, if we put x and v in terms of an initial condition, then we get these two new equation. And now we can put this into a metric and row reduce to get. From this, we get that value of C1 and C2. The position function after the bungee jumper has gone past the equilibrium point of the chord is this equation. Alternatively, we could have made solving the initial condition on the second equation easier by saying it starts at time 0. The constant C1 and C2 would turn out different, and the T would have been replaced with T 2.67. The equation would still have the same, and this turned out to be easier because all our exponential terms go to 1, all of sine terms go to 0, and all of the cosine terms go to 1.
There are three forces acting on the jumper when they are under the influence of the buggy. First is the force of gravity, which is implied mg. Second, there is the force due to the buggy, which is modeled after a spring with a force F equal to negative kx, with k being the spring constant of the buggy cord. Third, the force of the wing resistance, which is a wing resistance constant beta, whose value is determined above in equation, which has a linear relationship with the velocity of the jumper. The calculation involved in finding the true value for beta are rather complicated and beyond the scope of our understanding, so we will use the calculate constant. And the force we will get F gravity minus kx minus beta v equal to F net, where negative kx is the force of the buggy on the jumper and beta v is the force of the wing resistance. It makes sense that as a magnitude of kx and beta v increase, they will inevitably overcome the force of gravity. When this happens, the jumper will be at the end of the downward motion of oscillation and will be shot back from the force of the buggy. Next, using a numerical solver to find the motion of the jumper. In order to get the correct motion of the jumper, we need to find a way to model the position as they move up and down due to the buggy cord after their leap. Using the origin as the equilibrium point of the weight buggy, when x more than 0, the motion of the jumper can be modeled as the sum of the force equals the mass multiplied by the acceleration. To model the oscillation, we will treat the buggy cord as a spring and apply Hooke's law to model the force of the buggy on the jumper. Hooke's law is used for calculating the force imparted by a spring on an attached object and is defined as F equal to kx, where x is the displacement of the force. The spring constant k is given by dividing the force in Newton by the displacement caused that amount of force. In order to find an equation of the motion of the jumper, the equation above must be broken down to components that make up each force, which is mg minus kx minus beta v equal to ma. Moving the term around, we will get the expression introduction modeling the motion of free fall. Below d equilibrium, solving without a numerical, we will get x prime prime plus beta over m x prime plus k over m x equal to g. This gives a differential equation with a forcing terms g, which can be solved with relative ease. We must have two first order differential equations to relate to one another. This equation we found using the following steps. First, substituting A equal to beta over m and B equal k over m, and isolating the x prime prime, we will get x prime prime equal to g minus a x prime minus b x. Now, the next step is to create two first order equations, which is y1 equal to x and y2 equal to x prime. Now, we plug y1 and y2 into our equation with the addition of y prime 1 equal to y2, and we will get y prime 2 equal to g minus a y2 minus by1. When a and b are substituted back into the equation we will get y prime 2 equal to g minus beta over my2 minus k over my1. Now, these equations are useful to see how the different parameters affect the motion of the jumper.